What did you think of that quiz? What did you think of the quiz? Was it hard or what? So problems 1, 3, and 4 are all the same problems, basically. They're all the same thing. You just draw some triangles and you figure out what the other sides of the triangle are, and then just do all your ratios, SOHCAHTOA, and then flip all those over. Hopefully that was okay for you. I mean, those were all homework problems pretty much, right? Number 2, convert to radians. You needed to know the conversion. So you needed to know to multiply that by what? Pi over 180. In terms of level of difficulty, out of 10, 10 being the most difficult, like a very tough problem that you'd see on a quiz, I would say this ranks somewhere around a 1 or a 2, and these rank somewhere around 3s. 3s, maybe 4 if we're going to push it. That's the quiz I was going to give you. Okay? So that's part of why I wanted to do this. I wanted to see what your expectation of yourself and your classmates would be versus my expectation of the class. So the homework is always there to help you learn what you're doing. But the quiz, this quiz should be almost an extension of that. It's more than just the homework. It's, do you understand these concepts? So let's take a look at this over here, because I think it's worth talking through a little bit. Find the equation of the circle. So you would have had to have known the equation, x minus h quantity squared plus y minus k quantity squared equals r squared. You would have had to have known that. Then you would have needed to know that I gave you hk, the center. Then you would have needed to use this point how? To figure out the radius. So you would need to know how to find the distance between 2 points, which is a quiz you had when you were asked to go home with that, right? Now the fact that I gave it to you as a home assignment does not mean that I would expect that you could only do that problem at home. Especially because I gave it to you as a home assignment, that should be something that you should now be able to do, right? So I thought that was a fair question. This one, that one we can just write the answer up on the board while I've got it up here. So does anyone know the way you could represent all the angles shown here using that n? N over 2, pi? Missing the pi. Pi over 2n, something like that. So what you would have needed to see here is that you've got the angle 0, pi over 2, pi, 3 pi over 2, 2 pi, and that basically you're starting out at 0 and jumping by how much each time? 90 degrees or pi over 2, right? So you just need all the multiples of pi over 2, and that would give you all those angles. And we talked about that in class, right? Okay, so that I thought was fair. Now, number 3 is very much like numbers 1, 3, and 4 here, except I did it with a picture instead. And I gave you 2 angles alpha and beta and asked you to find cosine alpha plus tangent theta. Did I say beta? Sorry. I gave you alpha and theta. Asked you to find cosine of alpha plus tangent of theta. So I don't think you ever had a homework problem that looked like this. But that doesn't mean that it can't be done. How do you find cosine alpha? We have to find this side, don't you? So how do we find this side? We square that one, we subtract. So it would be like this side right here is the square root of 144 minus 49. Whatever that is, right? So cosine of alpha is which side over which side? And what's the adjacent side for alpha?
Square root of 144 minus.
Yeah, it's this one, right? So this right here would have been this over this. What is this? What is that? 51? I can't do basic math. 50, 90, or 95? Root 95? Yeah. I think it's root 95. Root 95. So this would have been root 95 over 12 plus what's tangent? of theta. Tangent is which side over which side? Opposite. This is the opposite side to theta over the adjacent, which would have been root 95 over 7, right? And then you would have had to put these together with a common denominator. So you would have had to multiply this by 7 over 7, and this one by 12 over 12. So I'm pushing, this is pushing further than a homework problem, right? This is a little bit more, but the actual mechanics is...
What is that grade?
These all probably like 7s, you know? And then the last one, 7s, 8s. But that's why I didn't give you this quiz, because I felt like we needed to establish this first, like my expectation versus your expectation.
Would we have had the same amount of time?
You would have had more time. Yeah, you would have had more time on this. And I may have only have given you 3 of these. These are the ones I had listed down. Runner going around a circular track, radius 120. It takes, sorry, it's supposed to say, it takes 14 minutes to complete 5 laps. What is the runner's linear speed? So you have to know the formula, and then angular speed, you have to know the formula. So that's very much like a problem I did in class. So if you look at those problems, I would say 3 of the 4 were, well, at least 2 of them were class stuff we did in class more than on homework, right? Number 2 for sure. Number 4 probably more something we ended class with as opposed to you saw in homework. Okay? All right. I think we might do this again, where you break into groups, and maybe we'll get better at it. I don't mind continuing to do this, but this is not what I'm looking for, and this is not anything personal to the group. It's just this is basically you setting the bar for yourself, like right here. That's my bar. Okay, let's try and find some place agreeable in the middle. Right? Where you're in here, and if you're going to make a quiz for your classmates, you're going to challenge your classmates, but you're not going to be unreasonable. But you're also not going to just give them something that's going to be super easy. Next time if we do this again, and I get a problem like this, I just won't put it on the quiz, right? Okay. Any thoughts? I mean, I'm just trying to find ways to help you, does this seem reasonable? Try this again maybe one more time and see how it goes? Any thoughts? You just want me to make the quizzes and give them to you, or you want to have some participation in it? Yes? Okay. Okay. All right. All right, so look, why don't you, at the end of class, you can take a picture of that board. Why don't you do number 1 and 4 at home and turn that in to me next time? And what I'll do is I'll take this grade and I'll combine it with that grade, and that'll be your overall grade. All right. Now we pick up where we left off. I'll go ahead and pass the sign-in sheet around now before I forget. And start off on that. All right, so last class, I think we stopped when we were talking about those triangles, didn't we? We were doing the trig functions off the triangles. So we have already established SOHCAHTOA, right? SOHCAHTOA, and that sine, by definition, is opposite over hypotenuse and all that stuff. Now what we're going to do is we're going to talk about some additional identities. So some fundamental identities. Y'all seem bummed out. Are y'all okay? Are y'all all right? Y'all seem kind of, like y'all looked at that and now y'all seem all sad. All right, so here are some fundamental identities. The first ones are called the reciprocal identities. You don't need to memorize the names. The reciprocal identities are cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And then that's it, just those two. So what I'm doing here, the difference between this and last class is that last class I said sine of theta is opposite over hypotenuse, right? Working off of a right triangle. Here's theta, here's the opposite side, here's the hypotenuse, and here's the adjacent side, right? So working off a right triangle, theta being here, this is the adjacent, opposite, hypotenuse, and we defined sine theta to be opposite over hypotenuse. We defined all of them, didn't we? But every one of them, when I defined them, was in terms of these sides. The difference between that and this is that notice that this doesn't say anything about hypotenuse or adjacent or opposite. It's making a relationship between cosecant and sine, and that they are reciprocals of one another. So cosecant of theta is 1 over sine. You could also say that sine is what? 1 over cosecant theta. So they're just reciprocals. Tangent theta, these are called the quotient identities now, is that tangent theta is 1 over cotangent theta. And you could also say that cotangent theta is 1 over tangent. I'll go ahead and write up here back at the reciprocal. I'll write those other ones. Sine theta is 1 over cosecant. And I'll put that cosine theta is 1 over secant. So let me show you how you could use something like this, all right? I don't like that one. No, I think those are pretty straightforward. Questions on that? Okay, we'll see this, trust me. We have a formula sheet that's full of identities. These are some basic ones. We'll use those later on as we're trying to simplify expressions. We'll be bringing those out from the toolbox. Now you get a new identity, which is called the Pythagorean identity. Actually, there's more than one. Pythagorean identities. So let's see if we can come up with these Pythagorean identities, instead of me just throwing them up on the board. All right, if I do this, this is adjacent, this is opposite, and this is hypotenuse, right? Yes? Then would you agree by the Pythagorean identity a squared plus b squared equals c squared that I could write this down? Adjacent squared plus opposite squared equals hypotenuse squared. Yes? All right, so if we have this relationship, then in mathematics, whenever we have an equation, we're always allowed to multiply both sides of an equation or divide both sides of an equation by anything except 0, right? So I'm just out of nowhere, and this is kind of, you don't see this coming, but I'm just going to decide right now to divide both sides of the equation by the hypotenuse squared. Okay? Is that legal for me to do that? As long as the hypotenuse is not 0, I can do that, right? So I'm going to just come in here right now and divide this by hypotenuse squared, divide this by hypotenuse squared, and then divide this by hypotenuse squared. Agreed? All right, what does the right side of this become? That's 1, right? All right, let's take a look at this adjacent squared over hypotenuse squared, and I think I'm going to write it over here. I'm going to go back over there in a second, but I just want to make sure you understand what I'm doing. When you have adjacent squared over hypotenuse squared, since they're both being squared, can't I rewrite it like that instead? Yes? It's like when you square a fraction, you can square each of them, right? So we're used to going like from here to here, but I can go backwards from here to here. So this is the same as adjacent over hypotenuse squared. What is adjacent over hypotenuse? Which trig function is that? Cosine. So this is saying cosine of theta squared, isn't it? And what is this one saying? Opposite over hypotenuse squared. So sine theta squared. So we get this fundamental identity that we can derive from the Pythagorean formula, a squared plus b squared is c squared. We get this right here. This is critical in this class. Now I'm boxing it because it's important, but that's not the version you're going to see in the book. The version in the book is going to look slightly different than this. Any questions on how I got that, though? No? Okay. Let me rewrite that the way the book has it. Okay, that's the book's version. Now we have to understand a few things about the differences in these versions. Notice, first of all, that they switch the order, right? They put the sine before the cosine. Now they're allowed to do that because that's a plus sign, and addition doesn't matter, right? So that's fine. But then also these squareds, they moved them, didn't they? They moved the squareds and they put them right after the n here. They put a 2 there. Right after the s, they put a little superscript right before the angle, right? That is the accepted notation for squaring a trig function. We put the 2 here instead of putting parentheses and putting the 2 on the outside. So you need to understand that that's what that means. Now, here's where things get a little bit messy, I guess. If I say what is sine of, let's say, 3 squared like this, am I squaring the whole thing or am I squaring just the 3? Just the 3. So this is really saying sine of 9. Understand? If I write sine 2 here and then 3, this means you take sine of 3 first and then square the answer. Major difference between those two expressions, right? If it were up to me, we would just leave it like this. But the reason why they stopped doing this is because people would get lazy and they would forget the parentheses, and then you would think you're squaring the theta, right? And so just to be safe, I guess, they put the 2 right here so that you know that the sine part's being squared. All right? Questions on that? That's one of the Pythagorean identities. You have to have that hardwired, memorized, that one. Now, there are 2 others. So remember right here where I came in with this blue and I divided by hypotenuse squared? I said I just pulled that kind of out of the air? Yes? I can come up with the other 2 Pythagorean identities by changing what I divide by. Now, when I picked hypotenuse squared, I knew that hypotenuse over hypotenuse, that was going to become a 1, right? Could I create a 1 over here? Okay, how could I create a 1 on the left side? Divide by adjacent squared, or opposite squared, my choice. So let's start with adjacent squared. What if I do adjacent squared here, adjacent squared here, and adjacent squared here? What would my new formula become? What would I get? This would become what? 1 plus, okay, if you're doing the opposite over adjacent, what trig function is that? Opposite over adjacent. Tangent, right? That's tangent squared. So this will become tangent squared theta. Notice again I put the squared here. And then equals, what is hypotenuse over adjacent? So hypotenuse over adjacent is the opposite or reciprocal of cosine, right? It's switched. And what's the reciprocal of cosine? Secant. So this is secant squared. And this is your second Pythagorean identity. 1 plus tangent squared theta is equal to secant squared theta. And then finally, I could have divided everything by what? By opposite squared. So if we come up and we do opposite squared, opposite squared, opposite squared, and opposite squared, we get our final one. Okay, that's the one we just did. Now if we do this one, adjacent over opposite is the reciprocal of tangent, isn't it? Which is cotangent. So this should be cotangent squared theta plus opposite over opposite, 1, equals hypotenuse over opposite. Hypotenuse over opposite is the reciprocal of sine, isn't it? So cosecant squared. There they are. Those are your 3 Pythagorean identities, with the first one being by far the most important. You've got to have that one burned into the brain. I may have mentioned this to you before, that I'm not a real big memorizer. Like when I was a math student, I didn't like having to memorize like hundreds of formulas. So any time that I could, I would try and become a little more efficient. So like if you have trouble memorizing all those formulas, instead just memorize this one, okay? Now, if you memorize this one, you can come up with the other 2 pretty easily. I'll show you how. You just see if you can do this mentally. Take everything and divide everything by sine squared. What would this over sine squared be? 1. What's cosine over sine squared? Cosine over sine is tangent, right? So, wait, cosine over sine? Let me do it. Sine squared theta, sine squared theta, sine squared theta. There we go. So what is this? 1? Yes? Plus, what's this? Cosine over sine is tangent flipped, which is cotangent squared theta, and then what's 1 over sine? Cosecant. And that's this one right here, isn't it? It's flipped over. I mean, it's changed, but do you see how I could come up with that formula just from this one? And then, are you sure you all see that? No? Okay, on the board just a second ago, I put the quotient identities. What were the quotient identities? That cotangent theta is 1 over tangent, right? Yes? Okay. So when you say cosine over sine, right? Cosine over sine. No, wait, did I put that up there? Hold on. Maybe that's why. No, that's not what I put up. Who has it? Did anyone write it down? No. Did I write this down? Yes. Oh, I did. Okay, I wrote that down. That is right. It's not wrong. But let's add something to this. Cosine theta over sine theta. I'm sorry, I left that part out. Because what is tangent? That you have to know from last class. Tangent is sine over cosine. And when you do 1 over that, it flips it and becomes cosine over sine. Maybe I'll be very clear on this. Tangent theta is sine theta over cosine theta. Cotangent theta is cosine theta over sine theta. Okay. There. See this? Those you have to know. So when I'm here at cosine over sine, that's this is cotangent, and then it's squared. Does that help? That's where this comes from. It's a lot of formulas. I get that you have to, start cramming a lot of information in your head, but. And then 1 over sine we said was the reciprocal of cosecant, right? So this is cosecant, sorry. All right, however you memorize those three, you need to know them, okay? If you want to use a shortcut like that, but it sounds like I'm confusing you more by doing that. So there they are, Pythagorean identities. All right, let's proceed. I think that's all. I just want to make sure I'm out of this section, that I don't want to do anything else. I'm good. All right, let's move into the next section. And we're going to go to 7.3. Computing the values of trig functions at acute angles. So an acute angle are between 0 and 90 degrees. Or you could say 0 and pi over 2 in radians. So what we're going to do is we're going to focus all of our attention in this section on a very special scenario where the angles that we're dealing with are acute. And then in the next section, we're going to allow our angles to get bigger than that. So to do this, we have to use something about that we already talked about, which was there are common angles that we all need to know. There were, do you remember what they were, the common angles? Need to know the trig function values at the common angles. And when I say no, I mean memorize. We have to memorize the trig function values at the common angles. We have to know what they are. So if I draw a triangle, a right triangle, and we call this angle here theta, and I tell you that theta is 30 degrees, which is what in radians? Pi over 6. So back when we were drawing these, we had cut this in 30, it was 45, and it was 60. Those were our common angles, 30 degrees, 45 degrees, 60 degrees, and then 90 up here, right? So we had 0, 30, 45, 60, and 90, right? And then we kept going around, but we're only going to deal with acute angles. So we're only doing angles in here, and we're going to look just at the common ones. So let's say that this angle is 30 degrees. Then we need to memorize the values of the 6 trig functions at that angle. And that means someone has to tell us what they are. So I'm here to tell you that sine of 30 degrees is equal to something, all right? Now, what is the definition of sine? Tell me what the definition of sine is. Going back to that Indian girl. It's opposite over hypotenuse, right? It's opposite over hypotenuse. So here is opposite, and here is hypotenuse. If your angle is 30 degrees, then when you take this side and divide it by this side, you are going to get a number. And that number is going to be 1/2. Always. I am providing that as a fact to you. Sine of 30 degrees is 1/2. Now what's kind of interesting about this is that I drew that triangle and I said that was 30 degrees. Somebody else could have drawn a triangle that looked like that, and that would still be 30 degrees, right? And somebody else could draw a triangle that would have been like that, and that would have still been 30 degrees, right? All 3 of those triangles have the same angle over there at 30 degrees. Agreed? What this is saying is that if I take this opposite side, we'll call this opposite 1, and I divide it by this hypotenuse 1, which only goes from here to here. If I take this side and divide it by that side, I'm going to get this number, 1/2. Always. And no matter how somebody draws this triangle, as long as they're using 30 degrees, if I take that side and divide it by that side, I'm going to get 1/2. Which means, if I just were throwing some numbers in here, this could be 5, and that would have to be what then? This would have to be 10, right? Or if this was 8, this would have to be 16, right? No matter what, as long as it's 30 degrees, the ratio of opposite to hypotenuse is 1/2. Okay? You're going to have to take that on faith, but that's the way it is, all right? Now, what is sine of 30 degrees? I mean cosine. Cosine of 30 degrees, again, is something that you're just going to have to take on faith, but unfortunately, it's not a number that's as pretty as 1/2. It is √3 over 2. Whoa, what? It's √3 over 2. That's a little bit harder to understand. So someone on their calculator real quick, take the square root of 3 and divide it by 2 and tell me what number you get.
0.866.
Okay, so this is approximately 0.866. And this one up here was exactly 0.5, wasn't it? So again, back to sine, the ratio was 1/2, 0.5, meaning this side divided by this side. This should always be half of this side, right? Or you could say this is double this one, yes? But if you do cosine, now you're doing which side over which side? Adjacent. So if I'm now measuring this side, the adjacent side, and dividing it by the hypotenuse, the ratio is no longer 1/2. The ratio is √3 over 2, which is what? Like, oh, it's about 0.86. 0.86. That make sense? The √3 is what kind of throws everyone off, because it's √3 is a weird number. What do we call √3? It's a special type of number. You'll know what root 3, root 2, pi, all those numbers have in common? I think I just heard it. What?
Irrational.
Irrational. All these numbers fall into a category of numbers called irrational. And what does that mean? What does it mean for a number to be irrational? It means you can talk to it, it's just going to ignore you. You know, you're like, hey, do this. They're like, do the opposite. You know, just completely irrational. Now, what does it mean to be an irrational number? Anyone know? It can't be a fraction. That means these numbers are not fractions. And this is something, we're going to go a little bit off on a side note here, but I think it's important as people of mathematics to know that I believe this, and you may believe this also, that if you just take a number line, and let's just look at the numbers between 0 and 1, right? And pick a number out of here. There you go, just a random number. There it is. Is there a way to write that number as a fraction? Like, I know that there is a number in here, 3/4, right? 3/4 is in here. And there are how many fractions in here? How many fractions do you think are in there? Infinite? There are an infinite number of fractions. I'll give you hopefully a very quick way of showing you. 1/2's in there, 1/3's in there, right? 1/4's in there, 1/5, 1/6, 1/7, 1/8. There's an infinite number of fractions in there, isn't there? The question, though, is if you randomly pick a number, is there a fraction that is equal to that number? Or are there numbers in here that are not fractions? And it turns out that there are numbers that are not fractions. And those are called irrational numbers. The problem with it is that we usually only give you a couple of examples. You're like, here they are, and so you think there's just a few. But it turns out that there's actually an infinite number. There are an infinite number of irrational numbers in here also. So you've got a mixture of non-fractions and fractions in that number line, just between 0 and 1. They're mixed in. Last question. I promise I'll get back to this. Last question. If I close my eyes and I reach in here and randomly pick a number, what do you think the probability is that it's a fraction? 50%? What do y'all think? So 50%, and then you said not very high? You think less than 50%? Okay, so let me get your reasoning behind 50% first. What's your reasoning? Okay, so you have an infinite amount of fractions, right? And I told you have an infinite amount of irrationals. So half and half, 50-50. Can you justify your reasoning on why you think the probability of me picking that would be less than 50%?
In between each rational number, I feel like there'd be infinite numbers of irrational ones there. I don't know.
Okay, I like that conjecture. That in between every fraction, every two fractions, there's an infinite number of non-fractions. That's your argument. Okay, I'm going to counter your argument by saying in between every two fractions, there's an infinite number of fractions.
I was thinking of what I meant, but I'll forget.
This is a good discussion. Look, let's say we have two numbers, A and B. Let's say they're both fractions. Then the number right in the middle, who was the people that I was trying to... How do you find the number right in between 2 points? Who was that last week? How do you find the number right in between two numbers? You add them and divide by 2. So you take their average. So if I take these two numbers, add them together and divide by 2, if these two numbers were fractions, when I add them, it's still a fraction, right? And if I divide by 2, it's still a fraction. So that is a fraction in between two fractions. But I could continue to do that. And every time I do that, I'm going to have more fractions. So between two fractions, there's an infinite number of fractions. But then in between two fractions, there's also an infinite number of irrationals. It starts to create headaches after a while, if you're not already there. So I'm going to give you the answer to the question, all right? If you close your eyes and you pick a number randomly out of this interval 0, 1, the probability that it is a fraction is 0. 0. Unless you went looking for it. Now that should make you like, this doesn't make sense. And here's the reason why. There's actually two types of infinity. There's what we call countably infinite, which would be like you're walking 1, 2, 3, and you walk forever, right? You keep counting. That's a type of infinity, but it's countable. And then you have what's called uncountably infinite, which is where you cannot get from one to the next without skipping an uncountable number of, it's impossible. So it's like the fractions you could look at as like lily pads, and there's a way to kind of like get across this pond on all the fractions stepping on lily pads. But if you try and go across the irrational numbers, there's no lily pads. It's like you take a jump to a lily pad and you realize there's a whole other infinite number of lily pads behind you. And I have a better analogy. If you've ever been out away from the city on a dark night, starry night, has anyone been out of the city and like gone like, oh my gosh, this is amazing. Like it's completely different when you get away from the city lights. Clear night, it's like, wow, you see the Milky Way, see all these stars. So when you're looking at a starry night like that, if you were to close your eyes and just point, if you had like a perfect instrument to point into a perfect line, and you pointed, what do you think the probability is that you're pointed at a star, exactly at a star? You're probably going to be pointing into darkness, aren't you? Yes? That's kind of like what I just said. If you go in there and you reach into that interval and try and pick out something randomly, you're not going to get a fraction. You have to actually like look at it and aim for it. The blackness in the sky is the irrational, and the stars are the fractions. Does that make sense? So, root 3 starts to mess us up because it's an irrational number, so we start to lose the connection that we have with this idea of 1/2, which is 0.5. That's something we can visualize, we can understand it. The root 3 makes things messy, but that's what it is, okay? The ratio of the adjacent to the hypotenuse is always root 3 over 2 if your angle is 30 degrees, okay? And then from here, the rest, all the remaining 4 trig functions can be found by just knowing those 2. So let's talk about the next 4 for this one. What would tangent of 30 degrees then be? So you only have to memorize these 2. So what is tangent of 30? Well, the definition of tangent, I just gave you the quotient identities, is sine over cosine, right? So if we want to know tangent of 30 degrees, we have to take sine of 30 and divide it by cosine of 30. What is sine of 30? Half, we already knew that. That was given to us. And we take 1/2 and we divide it by this, root 3 over 2. And now begs the question, how do you divide 2 fractions? Multiply reciprocal. So this means you take 1/2 and instead of dividing by that, you multiply by 2 over root 3. So division is the same as multiplication of the reciprocal. The 2's cancel, and you get 1 over root 3. That is a correct answer. That, however, is not the answer you'll see in the back of the book, because the back of the book is going to rationalize this. And although I told you last class I don't require you to, you should be familiar with, since this is a common angle, you should be familiar with what its value looks like at 30 degrees. So I am going to rationalize root 3 over 3, root 3, and then I'm going to there. That okay? All right, while we're here, let's look at the other 3. How about cosecant of 30 degrees, which is what is this? We're going to flip what over here? We're going to flip over sine, right? We're going to reciprocate sine. So we're going to do, instead of 1/2, we're going to go 2 over 1, which is just 2. And then for secant of 30 degrees, we're going to flip over this one. So that's going to be 2 over root 3 instead of root 3 over 2. But the book is going to rationalize this. So if you multiply the top and bottom of this by root 3, you'll get 2 root 3 over what? 3. And finally, cotangent of 30 degrees, which would be the reciprocal of tangent, wouldn't it? And I'm actually going to come back over here to tangent. Remember when we were right there? Before we did that? What's the reciprocal of that right there? Just root 3. So I could just do that right there, root 3. Okay, we good? Now we need to talk about 45 and 60 degrees, because those are the other two common ones that we need to know. Is anybody here planning on going to graduate school? Thinking about graduate school? Okay.
Probably.
You don't have to know right now, just if anyone has that plan. If I have some time later on this semester and y'all are trying to distract me and get me off on a tangent to slow me down or something, then you can ask me about the that interval between 0 and 1 again. I'll tell you a story about that. Graduate school, something that happened. All right, let's look at, let's do 60 degrees. I'm going to skip 45, I'm going to go to 60, because 30, then 60, those kind of came together, didn't they? So let's talk about sine of 60 degrees and cosine of 60 degrees. So I'm going to give these to you, all right? And that triangle looks a little different. Looks like this, 60 degrees. We still have adjacent, we still have opposite, and we still have hypotenuse. And remember, we're saying that it doesn't matter how somebody draws this, right? It doesn't matter how they draw that. We're always going to get the same ratio. So sine of 60 degrees is root 3 over 2, and cosine of 60 degrees is 1/2. That's just the opposite of what we just got, right? That's the opposite of what it was for 30 degrees. For 30 degrees, this one was 1/2 and this one was root 3 over 2, but for 60 they flip. And that's good news because it's less to have to remember, really, right? You just have to remember these two numbers and then which goes with which, right? So I'll just do tangent now. What's tangent of 60 degrees? So I'm going to take sine 60 and divide by cosine 60. And that's going to be root 3 over 2 over 1/2, which is root 3 over 2 times 2 over 1, and you just get root 3. And then do you think you could get the other 3 yourself? You're just going to take those and flip them over, right? So this one will give you, flip that one, we get cosecant. Flip this one, we get secant. Flip this one, we get cotangent. Handle that? Okay. There is a way that you can remember which goes with which, because I think that's the part that people get most confused with. It's like with 30 and 60, they know it's root 3 over 2, and they know it's 1/2, but they forget which one goes with which. So here's a way you can, let's see if this helps you remember it. Let me draw a triangle. If it's 30 degrees, it's going to look something like that, right? So you have to have some idea of what 30 degrees looks like. Do y'all agree that's 30? That 60 is bigger, right? Okay, let me ask you, which of these sides is bigger? The opposite or the adjacent? Which one's bigger? Adjacent's bigger, right? Adjacent here, I'm going to say is big, right? This one right here, opposite, is small. Yes? Now, the hypotenuse, I don't care about. I don't care about this. Because when I do sine, I'm doing this over this, right? And when I'm doing cosine, I'm doing this over this. So when you're at 30 degrees, your sine should be a smaller number over something, as opposed to the cosine, which should be a bigger number over something, right? So when you compare these two, 1/2 versus root 3 over 2, they both have the same denominator, don't they? Yes? So ignore it. Which of those is bigger, 1 or root 3? Root 3 is bigger than 1. This is bigger than 1. So in 30 degrees, the bigger side right here, this should be the cosine part. The cosine should get the root 3. And the smaller side should get the 1. Understand? But then when you come and look at this picture, they switch places. Now your opposite is bigger than your adjacent. So this side should get your root 3, and this side should get your 1. So root 3 over 2, 1 over 2. Understand? I mean, if it helps, it helps. If not, just memorize it, like I said. All right. Those are your 30 and 60. Now 45. And I think you're going to like 45. 45 degrees. So 45 degrees, the great thing about 45 degrees is that this side also should be 45 degrees because they have to add up to be 180. So if this is 90, that's 45, 45. Then that means that these two sides are the same length. So adjacent, opposite over hypotenuse and adjacent over hypotenuse should give you the same value. And that's how it turns out to be with sine and cosine. Sine of 45 degrees and cosine of 45 degrees are the same exact number. Now, unfortunately, the number is not pretty. It's not like 1/2 or anything like that. It's root 2 over 2. Root 2 over 2. Root 2 over 2. So you've got to memorize that one. Root 2 over 2. Irrational number. Now, what about tangent? Tangent actually is pretty nice. What would tangent of 45 degrees be? Be 1. Because you're going to take this one and divide it by this one. They're the same number. So there's no, you could do the flipping and all that, but it's just going to turn out to be 1. And then you could do, flip this one over, flip this one over. And how do you flip over 1? Well, it's just 1, right? So you just get the other 3 that way. Are we good? Sure? Okay. We're going to see now. We are going to see how you do with this. I would memorize those as soon as possible. Not like memorize it the day before the test. Like try and memorize those by next class, if not the latest beginning of next week. Here we go. Example. Here's a right triangle. This is 30 degrees. This is 2. Okay? Label, we'll leave that. Solve this triangle. What do I mean by solve this triangle? That means give me all the angles and give me all the sides. Okay? Give me every angle and every side on that triangle. That's all I'm providing you. So what can you tell me? What can you tell me here? What's something I can write down?
So the hypotenuse is double the 2 in this case, right? 4.
The hypotenuse is double this because that's 30 degrees. Okay. I agree. Let's see if we can't formulate that a little bit different. It's good that you have that, but let's see if we can't like use the information in what I gave you to try and formulate more of a process to get to that. Okay, so what do we know about 30 degrees? We know sine of 30 is what? Is 1/2, right? We do know that. And if we just look at this as a triangle, let's label this side H and let's label this side A, okay, for adjacent and hypotenuse. Is that okay? By definition, what is sine of any angle? On a right triangle, what's sine of any angle? Not sine of 30, but what is sine of any angle? In terms of the sides, it's what over what? It's opposite over hypotenuse, right? Okay, so what is opposite over hypotenuse on that triangle? 2 over h, right? You all with me? So that means that sine of 30 for this particular triangle, if it has to be equal to 1/2, and sine of any angle is 2 over h, then don't you agree that these two have to be the same? Yes? Now, I understand that just saying that that's double that, I understand. You had 4 already. But this is going to be more useful, especially with the problem I'm about to give you, because you're not going to be able to just look at it and say double that. Okay? Do y'all see where I came up with that equation? All right, now solve for h. So let's get h out of the denominator. We'll multiply both sides of this equation by h. And won't that get it off the denominator over there? You all right with that? So this just says now 1/2 h equals 2. And multiply both sides by 2. And you get the same result, right? H is 4. So now I know this is 4, don't I? Questions on that? Now's the time. Using the fact that this tells me what our ratio needs to be. Our ratio needs to be 1/2. But sine says on this triangle 2 over h has to be equal to that ratio. So then we solve for h. And now?
Would it work the same
If
if you were trying to find A?
you were trying to find A, yes. But you would have to use a different trig function for that. Yeah, you would have to be, let's do that, but let's just get through this right now. Can we finish solving this triangle? I know what h is. I know what h is. Can I figure out a right now? Yes, because I know that a squared plus b squared is c squared. So I can go to the Pythagorean identity now, and I can just say a squared plus 2 squared must equal 4 squared. And so a squared plus 4 equals 16, which means a squared is 12, which means a is root 12, taking the square root on both sides. So this is root 12. And did we know what the other angle was in that triangle? So it's got, this one has to be 60. So we've completely solved the triangle. We have all the sides and all the angles. Are there any questions on how I got that? Okay, let me give you another one. How about this one? How about there we go. So I'm not quite sure you'll be able to shortcut this one. I mean, you could, but it's not as intuitive as doubling that 2 was, right? I remember giving a problem just like this on a quiz last semester, and everyone missed it.